All right, so good morning, everyone. I'm Curtis Seaman. For those who don't know me, I'm a member of the VIIRS Imagery team, and one of our duties is to make sure all the VIIRS imagery products are working right. And we've also been involved in getting the near constant contrast imagery product into AWIPS. And so today I'm going to introduce the product and show a few examples of what it is and what it does. All right, so simply put, the near constant contrast imagery product is a way to display VIIRS day-night band imagery in AWIPS. And for those of you who've seen day-night band imagery before, you'll probably know that there's a lot of different methods for displaying the day-night band. And this is due to the fact that the day-night band itself is sensitive to very low levels of visible light, 7 orders of magnitude less than what you typically see during the day. And so the day-night band provides visible imagery at night, but because it's sensitive over this 8 order of magnitude range of radiance, it's very difficult to display it as an image when you only have 256 colors, or in the case of NAWIPS, you only have 96 colors. And so the near constant contrast product converts the day-night band radiance into a pseudo albedo that provides nearly constant contrast for daytime, nighttime, near terminator scenes, and it works for all phases of the moon. But it's not a true reflectance. It's called a pseudo albedo. And albedo, the albedo of an object is constant no matter how much light is hitting it. But the near constant contrast product does not provide a constant albedo based on the way that the algorithm works. And so it's not a true albedo like the day-night band lunar reflectance product, which I know some of the forecast offices are receiving. And these NCC values will vary throughout the lunar cycle, and so you have to change the scaling within AWIPS in order to ideally scale near constant contrast imagery. One of the main benefits of near constant contrast imagery is that it's operationally supported by the JPSS program, and it does provide value even when there is no moonlight, unlike the day-night band lunar reflectance product. And so these are 2 examples here. On the left you have the near constant contrast imagery product. On the right is a day-night band lunar reflectance product. And this is for a case where you have available moonlight, where the moon is above the horizon when VIIRS is passing overhead. And this is a scene off the coast of California. And you can see that the near constant contrast imagery is nearly identical to the lunar reflectance product. But another case, for when the moon is below the horizon, you can see that the near constant contrast still provides imagery when the lunar reflectance product doesn't work, because the lunar reflectance product requires there to be moonlight. And so this is one of the main benefits of near constant contrast imagery. Now, as I said, the near constant contrast imagery values that you'll see in AWIPS, they change as a function of the lunar cycle when you're looking at nighttime imagery. And so a great resource to find out about the moon phase is this link that I've provided. And we can go to here's an example of what the website looks like. Shows you how much moon is available for any phase of the moon, or the current phase of the moon, I should say. But the thing to note is that because VIIRS orbits at around 1:30 a.m. and p.m. local time, that the moon is not always going to be above the horizon even when when it's not a new moon. So basically, between last quarter and first quarter, there is no moonlight, except for the fact that because the orbit is at 1:30 a.m. instead of midnight, the amount of moonlight actually shifts a couple of days. So what we say is that the moon will be below the horizon if you start from 2 days after a last quarter moon, and you'll have no moonlight available until 2 days after a first quarter moon. So it's about a 2-week period where you'll have no moonlight, and then the next 2-week period you will have moonlight. And starting next week, we are going to be having moonlight for the NCC imagery. And the image quality definitely improves when there is moonlight available. Now, if you pull up NCC Imagery and AWIPS, you'll probably get an image that looks something like this. And if you've ever looked at day-night band imagery before, you'll say, this doesn't look like any day-night band image I've ever seen. Why are all the cities black? Well, this is a problem with the default display in AWIPS 2, which set the top of the color scale, the top value, is set to black. If you reset that top color in the default color table to white, then it'll start to look like day-night band images. Now you also see that these white lines show up at the boundaries of all of the VIIRS granules. And these are a known display bug in AWIPS. This is not actually a problem with the NCC imagery itself. It's something that needs to be fixed within AWIPS. But if you zoom in far enough, these lines will disappear, and you won't notice them. Now, I want to talk a little bit about proper scaling of the near constant contrast product. The default scaling scales these pseudo albedo values from 0 to 1.6. But the actual product itself gives values on a range from -10 to 1,000 to account for the fact that their light sources like city lights can be 3 orders of magnitude brighter than what you'd expect to receive from the moon. And the default scaling works fairly well, but we would argue that for most cases, a scaling from 0 to 1 actually works a little bit better, makes the clouds and snow features a bit brighter. And so we have details on how to adjust the color table in AWIPS to improve this display on a quick guide that we've submitted to the VLab, and I'll have a link for that later on. Now, for some places where you get away from city lights, if you have no moonlight, the clouds can still appear pretty dark. If you look down here over, say, New Mexico, there are some clouds over there that are kind of difficult to see. If you really stretch the scaling to something like 0 to 0.5, these clouds start to show up more. Although you can see most of the clouds and snow in the Midwest are now saturating the color table and making everything appear white. The other thing that will happen when you lower the maximum value is that city lights will actually appear to expand, like the cities are getting bigger, because more and more areas around the cities will be bright enough to exceed the maximum value on your color table. Now this is a case where we have available moonlight, and you can see that there's actually very good contrast between the clouds and the background surface. and you'll notice that the cities appear to be sharper and more distinct. And this is what will happen when there is moonlight available. And so this is the kind of imagery you can expect during times when there is moonlight around.
Yeah, quick question.
Yes.
Yeah, well, I was trying to see the date on that, but it was pretty tiny. When was that? The one before?
It was from November 27th.
Oh, yeah, okay, thanks. Yeah, I see the plot. Yeah, are you going to say a little bit of something about how the labeling works, the timing, the date stamp?
I believe it's based on the... Is it based on the beginning of the orbit when it passes over the... I think it's the time is the first granule, the start time of the first granule as it passes over the United States.
Okay, so the very first scan.
Yeah.
Okay. Thanks.
And
ascending or descending?
both. Well, it'll be descending at night and ascending during the day. And it'll take about 5 minutes or less for VIIRS to pass over the United States. And so here's another case where we have moonlight available, and we've zoomed in far enough so that those annoying lines are missing from the image. And you can also see how distinct the city lights appear. And there's a lack of noise in the bare ground, as when the moon goes away, the bare ground will appear much more noisy than this. Here's a interesting example looking at Florida. This is another case where there is no moonlight, and one of the things that you'll notice along the coast of Florida, you'll see that the city lights actually appear to extend out over the ocean. And this is a consequence of these city lights being covered by clouds, that the clouds will actually scatter light back to the satellite over a larger area than just where the city lights exist. And so this is one of the ways that you can tell that there are clouds around, even if they get drowned out by the brightness of the city lights. The edges of the cities will look much fuzzier and will cover a much larger area than they do during clear sky conditions. Here is another example. This is from November 30th, where we did have moonlight available, and you can see an aurora up here in Canada. And again, this aurora has values actually much greater than 1, so it just appears solid white up here. One of the other interesting things about this case, though, is you can see one of the main advantages of having near constant contrast imagery, that you can see these low clouds over the state of Washington that are even extending up into all the different mountain valleys. And you can compare that with the snow-covered mountains of British Columbia and Alberta. And even down here in Wyoming, you can see that the mountain ranges are actually sticking up above the low clouds. And you can see these bright lights here in western North Dakota. These are actually gas flares from all the oil operations in North Dakota. Now I've taken that previous image and rescaled it from 0 to 1.6, which is the default range. And now you can see that the aurora does not saturate nearly as much up here in Canada, but we've made the rest of the clouds and the snow appear darker. And so we encourage all the users of the NCC to really play around with this scaling and figure out what works best for you when it comes to picking out things like like low clouds or snow, or if you're interested in city lights or auroras, for example, you'll want to adjust the scaling maybe even higher than 1.6. And so,
I got a question for you. If you go back to that.
sure.
Yeah, this is Schoberg. So is that the Hudson Bay up in the upper right?
Yeah, right here. This would be the coast, or the edge of the ice in Hudson Bay up here.
Yeah. So that you would think that is ice, right? That's what I was thinking too.
Well, I would say to the west of that looks like ice and snow, and then you have some open water, and it's hard to tell from this image if that's ice actually in Hudson Bay or if those are low clouds. You'd have to zoom in much further than this to be able to tell.
Okay.
And so just the last slide, I have some typical ranges here that you can expect to see for different features of interest. You know, when you have moonlight available, clouds and snow are going to have values that are pretty close to 1. Although, you know, snow may be darker if it's mixed in with tall grass or in forested areas, of course. But when the moon goes away, clouds and snow, the values actually decrease. And so clouds and snow will have values much closer to 0.5. But city lights and auroras, actually their values increase when you have no moonlight. And this is based on the fact that the NCC is normalizing based on the expected amount of moonlight. And so you take the radiance from the city and you divide it from the expected radiance from the moon. As the expected radiance from the moon decreases, you're getting a smaller and smaller denominator. And so that ratio gets larger and larger. And so city lights may have values that approach 1,000 when you have no moonlight. But when there is moon, values are closer to 5 to 10, although maybe extending a little bit above and beyond that depending on what you define as a city. And in the same way, the values for auroras increase when the moon goes away. And bare ground is much easier to distinguish from water when there is moonlight, because you'll have reflectance values that are around 0.25 or 0.3 or so. But when the moon goes away, bare ground is generally within the noise of the NCC product, and it'll look very speckled. And so, again, we encourage users to scale the product accordingly to what you're interested in looking at. And as I said, we put out a quick guide that discusses how to adjust the color tables in AWIPS 2 to be able to improve the display from the default version. And there's a link for that down at the bottom. And
can you click on that?
It won't. I'd have to log in.
Yeah. You have to be logged on to VLab for
It doesn't go there.
Okay.
for that link to actually show up. And currently we don't have an account for this page on VLab yet.
Say something about
Well, can I ask a question? I thought Dan or Bernie there do have a. Pretty sure Dan
I
it.
tried it earlier, Tony, and I wasn't able to get through. I don't know if that means I need to be a part of that community or not.
Oh,
No, you don't need to be part of the community. This is Eric, and that's a public-facing page.
Okay.
See how it says web, and usually it'll say nncep.noaa.gov/group if it needs to be a part of the community/web. The issue is, I believe that this is all in caps and it's case sensitive, so it needs to be lowercase.
Okay.
But I will also say that we haven't yet populated this link with the full quick guide that Sierra provided. So if you click on the link, there's some stuff in there, but it's not what I think they're hoping to show.
But it will be there eventually, right?
Oh yeah, no, I plan on doing that in the next day or two. It's just a matter of, there's a lot of images you guys had, and it's complicated. You can't. It's HTML. I can't just upload it. I have to do it manually, and that takes some time.
All right.
Hey, are you guys generating this product over Alaska by any chance?
Yeah, there should be an Alaska sector.
The Alaska data has been flowing since before CONUS.
Okay, great. Thanks.
Yeah, but Scott, is that near constant data or just a day-night band?
That I'm not sure of.
Yeah, hi, this is Lee from the Office of OBS with Eric. The imagery was flowing over Alaska well before the day-night band, but the day-night band implementation was for everyone at the same time, just over the last week or two.
Okay.
All right, thanks.
All right. The other thing I want to make sure to mention is that the latencies for NCC data around hour and a half or hour and 40 minutes or so from between the time that the satellite collects the data and the time that it shows up in AWIPS.